Hi everyone, welcome back to my control system video. In this video, I'm going to explain how do we use the Nyquist plot to determine the stability of a system. We will consider a standard systems with the forward transfer function Gs and with the feedback transfer function Hs. These two will form the closed loop system that we are going to use it to evaluate the stability using the Nyquist plot. As usual, this Ts will denote our closed loop transfer function, which is constructed from Gs over 1 plus Ghs. We have learned that in the root locus analysis, to determine the stability of the systems, we are basically evaluating this 1 plus Gs, which is our characteristic equation. We need to find out the roots of the characteristic equations and to determine the system stability based on the number of closed loop poles located on the right hand side of the S-plane. We will stay for the stability of the system. We need to determine the closed loop poles, which is equals to roots of 1 plus GHS. And this would mean that roots, which means that I'm setting this 1 plus GHS equals to the 0. And as we all know, GHS will be fractions. So we are taking the numerator of 1 plus GHS and equate to 0 and find the solution. Basically, we are actually saying that this is equals to the zeros of 1 plus GHS. Here is the complicating parts over here that a lot of us will be quite confusing when we are dealing with the Nyquist. Because in Nyquist, you have to remember, basically, if you want to find out the closed loop poles, we are actually determining the zeros of 1 plus GHS. So take note of this part. It is very important in the Nyquist stability criterion afterwards. For stability, we say that they should not have any closed loop poles on the right hand side of the S-plane. So that would mean that they should not have any zeros of 1 plus GHS on the right hand side. With this, now our question is, how do we use the Nyquist plot to detect whether do we have any roots on the right hand side of the S-plane? Again, just to make sure that everyone understands the same terms over here, this one that we are referring to will actually becomes the zeros of 1 plus GHS. And we must make sure that there is none of this on the right hand side for the system to be stable. So we need to find a way, relate this location or the number of the closed loop poles on the right hand side with the Nyquist plot. Because the Nyquist plot is the polar plot of the imaginary of GH omega versus the real part of GH omega. Based on this plot, we have to determine whether the system is stable or not. To be able to achieve this, we will need to use the Cauchy argument principles. Basically, it is talking about the mapping. How this argument principle works over here is that we will first consider this Fs as our transfer function, or any functions will do. And this Fs will have two zeros, s plus 1, s plus 5, which translate to the zeros over here, this and this. And we will have one complex quadratic equation, s squared plus 4s plus 5. And if we solve it, we will have our two complex poles here and here, located at -2 plus minus j1. And these argument principles actually describe that if we actually define a contour at the S-plane over here, which will be later transformed to a path in the Fs plane, by looking at the enclosure of the combination of zeros and poles, will determine the number of clockwise encirclement at the origin. The relation will be given as n equals to z minus p, where n is the clockwise encirclement at the origin, z is the number of zeros enclosed, and p will be the number of poles enclosed. Okay, we take one example over here. If we start from this point here, example, for whatever value that is representing this point, I substitute into this Fs, this point, goes into all the s terms. We calculate and return with a value that represents the map function fs, and this will translate to a certain point in here. If we jump to the next point and we do the same thing again, so that will translate to the other point, maybe somewhat here. If we do it repetitively, it become a path. Let's say something like this. And this path must be enclosed in a clockwise direction. So with this, I'm actually trying to enclose the first 0 at -1. So the resultant of this, according to this argument principle, is that if the path enclosed in the S-plane forms a contour like this that encloses the 0 over here, then the resultant map path will actually enclose the origin once, because the number of 0 enclosed is 1. If we enclose the poles like this, the number of the combination of the zeros and poles, z minus p, will be -2. Hence, in this case here, what this argument will say here is that it's going to enclose the origin in a different direction for twice. Perhaps something like this. One round, then 2 rounds. For better clarity, I'm going to demonstrate using some examples work on MATLAB so that we can see an exact running of these principles. Okay, let's start with the first example, which in this case here, I'm going to enclose 2 zeros. Basically, what you see over here will be similar like what we described earlier. On the left will be the S-plane, and you see the 2 poles and the 2 zeros are labeled over there. On the right will be the S-plane, where the contour on the left, okay, will be mapped to the path on the right. Okay, as you can see over here, the red lines represents the contour that actually we are trying to construct in the S-plane, and the resultant map path will be the blue line. As we are trying to enclose 2 zeros over here, we should be able to observe that in the FS plane, the map path will actually encircle the origin twice. Now we move to the next example, in which I'm going to enclose 1 pole. By enclosing 1 pole, if we follow the n equals to z minus p, so we are going to observe that the map contour fs will actually encircle the origin once, but in a different direction, which is the counterclockwise direction. Okay, in the last example, I'm going to enclose 2 poles and zeros, which means that the number z minus p will goes to 0, which means in this case here, the encirclement at the origin in the fs plane will be 0. You can see that the big box over here will enclose the combination which has the equal number of zeros and poles. The resultant map contour does not encircle the origin at all. If you are interested on how I do it, on how I animate the plot like this, you can visit my video in the code series. Okay, we come back to this. We are going to use this to extend it into our Nyquist stability criterion. Basically, we talk about the S-plane first. In the S-plane, if we are dealing with the frequency domain, basically my S will be transformed to j omega, which means that my real part is equals to 0. Our omega will always start from -infinity to +infinity. That means the path, it will start from here, -infinity, and it will go up to here, +infinity. By defining such path with an infinity points over here, basically we are also saying that anything on the right hand side of this along this path here will be all enclosed. That means we are actually enclosing all the roots on the right hand side of the S-plane, and this will transform to our Nyquist path as shown in here. And if we use the n equals to z minus p on the origin, basically it will not result in anything interesting. Simply because that the Nyquist is actually just showing GH omega plane, not the one that we want for stability 1 plus GH omega. So in this case here, this GH and 1 plus GH omega here is actually having a difference of 1. But there is no need to redo the plot since that the 1 plus GH and GH is just a difference of numerical of 1. So in this case here, instead of generating a new plot of 1 plus GH omega, we can make use of the Nyquist plot, but the point of interest we shift it to -1. So this will tell us about stability. And of course, we will have to rewrite the stability criterion n equals to z minus p by changing the clockwise encirclement at the origin into clockwise encirclement at -1 plus j0 point. The number of zero and close will tell us the number of closed loop poles, since we say that the zeros of 1 plus GHS will be equivalent to the closed loop poles. Hence, the number of Z actually tell us whether the system is stable or not. If Z is greater than 0, then the system will not be stable. While P will be the number of open loop poles, since the poles of 1 plus GHS is actually equivalent to the poles of GHS. With the new set of the stability criterion, we can make use of the Nyquist plot together with the information of the open loop poles, which is normally available at the start, to determine whether the system is stable or not. Okay, so that's all that I want to introduce in this video. In the next video, I'm going to show how do we make use of the Nyquist plot to actually determine the system stability. Thank you very much for watching. Bye.